The internet seems to be doing better. Hopefully it's working now. Okay. All right. So today we're going to start doing this the pattern analysis portion of the course. And ideally, I had wanted to. I actually did. I don't know if you guys paid attention to what I did here, but we used to have network and the spatial database lecture tied together. And I do still want to talk about this spatial SQL, and it ties in really well with what we did in terms of spatial joins and things like that. And it's like a totally different way of thinking about overlay and spatial joins, and so it's kind of neat. And I wanted to include that up in this portion of the course as well, but we're going to do it later because we're going to do it in another software package called QGIS. Anybody use QGIS before? So QGIS is an open source GIS software package, and it has a really good interface for doing spatial SQL. ArcGIS does have an interface for doing it, but it doesn't let you do spatial SQL on just normal data sets. You have to build an enterprise database and put your data into the enterprise database before it allow you to do spatial SQL. But it's an important. I think it's an important, neat skill to have, is to understand what spatial SQL is doing, and maybe I'm getting a little bit ahead of myself because I never really explained that. But when we do a select, you're doing a little teeny SQL, structured query language command. You're saying where this equals that. Structured query language, though, is much bigger than that. You can actually ask a table all sorts of questions, and you can say, I only want to see these columns, and I want to see how this table and this table are related to each other. And so we are gonna talk about that, but I need to make sure that the software is installed on both locations. Ben and I did that down here yesterday, so I just need to do it up in Hattiesburg. So we'll do that probably towards the end of the course. And now we're going to move on and do this pattern analysis, which is also very interesting. And it really does build on these concepts of spatial relationships that we've talked about up to this point, and establishing spatial relationships. So to do this, I do want to make sure that everybody's aware that there is this reading section in here, which for this one I think is even maybe, like, I don't know, more important. But I would like, I think that there's some good explanations in this open source reading that's available. I'm going to talk about most of this, but this will be a good section to read over. And some of this has to do with what we'll talk about today, and some of this has to do with what we'll talk about next week. Next week. Oh, by the way, my other class knows this, and I'll make sure that I post this on Canvas. But next week, I was going to fly into Gulfport. My ticket was to fly into Gulfport on Tuesday night, and they just changed my flight. So I'm flying into Pine Belt on Wednesday morning, and my plane lands at 11:15. This class starts at 11:30. So what I want to do is push the class back a half hour. I'm going to say next week, I'll post this on Canvas, next week we're going to meet at noon rather than meeting at 11:30. Okay? So we're going to meet a half hour later than normal. So if you come to class and nobody's here, remember that. I'll put it on Canvas. That's the case, and it'll be great.
So is this technically week? It would be technically week 7 because last week was our test, which would have been week 6.
Yeah, I guess that's right. Yeah, did I call it a different thing?
No, I label my notes, so I like to keep organized.
Yeah. All right, I think I'm actually going to start talking about this thing. So we're going to move on to discovering and examining spatial relationships using GIS as a tool. So really, we're doing spatial analysis, and we're using GIS as a tool to do that. And one of the things that will help us to start on our discussion is this concept of first and second order spatial effects. Okay? And I want to make the distinction between these two. So a first order effect in this example would be that something like as we get closer to water, as we go away, sorry, this is the gradient soil type. As we go away from a certain area, the observations change because of some underlying topography. It could have been water. I mean, they're probably all related. The presence of water, the soil type, and the trees are probably all related to each other. So as one variable changes, or as one spatial pattern changes, we could see how it changes another spatial pattern. There's all sorts of things like, next week I'm going out to write a paper with a colleague. I'm going to go to Utah. And as you look up the mountain, you can actually see the different types of trees change slowly as you go up. And finally, some of those tall mountains, they don't have any trees on the very top, right? They're above the tree line, is what they say. And so as you go up in elevation, in this case, I'm still talking about trees. I should find a better example, right? But the vegetation type changes as elevation increases. But there are other things that can change based on elevation. Last semester, well, here I'll highlight that at the end because I actually have a slide on it. Talked about those types of relationships.
Certain trees don't grow at a certain height.
Yeah, trees don't grow at a certain height for lots of reasons, but it's one thing that can be mapped is elevation, and our spatial relationship that we might find is the trees, the species change. Sometimes, depending on the geography, the trees may be the same species, but they might grow differently in different areas. They might grow taller. They might be fatter than they are in other places. And this could be even something like, well, like something very simple, like the presence of pollution means that certain species are affected and they're sick in those areas. So that's a first order effect in a spatial process.
Well, couldn't that be nutrient-based change too? Because
as nutrients.
You know, lose the nutrient that would have been on a normal platform.
Right.
So is like the difference between first and second, like, is it like the same as like almost like an independent and dependent variable? Like one is like a direct change. Is that like what's different between them? Like, because I'm reading the difference.
Yeah. So the difference between a first order and a second order is that first order effects are one variable's effect on another variable, and then second order effects are I think of clustering as one example of a second order effect. So it's the effect of the spatial pattern of one variable on itself. Okay? And so most spatial patterns tend to be, I shouldn't say most, but a lot of spatial patterns are cause clustering. So this one right here, especially in nature, like here we have a tree, and when a tree becomes established, it will propagate, and depending on its seed type, it propagates nearby. And so you expect to see an oak grow up and then create an oak grove because you have nearby oaks because the acorns fall down the ground and then they start growing oak trees. And even if they don't make it to maturity because they've got a big oak tree next to them, they'll grow big enough to make a little bit of oaks and they'll grow out. Okay. Now occasionally an oak will get an oak acorn will get taken a far distance by an animal and it'll start up and that'll establish another oak grove. Okay. grove of oak trees, or however you want to say that. But the second order effects are how that spatial process propagates and affects itself. An example of somebody who noticed this, that's not a environment, like this is a not a human geography problem, but a biogeography problem, but a human geography problem that somebody noticed. Have anybody heard of central place theory in one of your classes?
Yeah, I'm pretty sure.
Talking about the centrality of the arrangement of different types of species.
It's the arrangement of like human settlements.
It's like, and then it goes out, right? Like,
Yeah, so there was a scientist long ago, I forgot his name, sorry, but this is way back in the 1700s, 1800s, postulated that given like a flat surface of land that didn't have any other effects, we've got rivers and boundary effects, but kind of like the central United States, the Great Plains. He postulated that settlements would occur at a spread out fashion. So, you don't need a grain elevator every 10 feet along a track, right? It wouldn't help. And so you don't even need railroads everywhere. You just need railroads connecting the big cities, and the big cities have certain services. And those certain services will be spread out along the landscape. If they're services that involve servicing a lot of people, will be spread out fairly far apart. But then there'll be other towns, smaller towns, that have certain services, and you can almost predict what services will be available at what small towns and the average distance away from one town that has that service to another town that has that service. Okay.
It's kind of like the suburbs, like around like New Orleans. Like Slidell has a lot of shopping and stuff, but it doesn't have the university hospitals that New Orleans has. So they have different things.
Yeah, because of there's lots of things that involve it, but economic theory. But what I'm trying to say is some things tend to cluster, and some things tend to disperse at evenly spaced patterns, right? And some things are totally random.
So you're saying that a person have certain patterns of how this is not as if it's planned out. Yeah, you'll plan some things out, but some people just through living around others know what is required in that area. And so you assume that they're gonna have this, that. Now this is everybody living just like in a shack, and he's disconnected from the world. That's the outlier, but just people just in centrality of each other, they live a certain type of way. You can always see that same pattern wherever they go. Is that what you see?
Well, okay, there are people that make different choices, right? And some people love living out in the country away from people, and some people love living close by. But social sciences, one of the things that they'll often do is generalize and say, and sometimes by generalizing, you can establish a model and kind of predict how cities might grow in the future or things like that. And so that's what that exercise was about with the central place theory. It's not trying to, again, that's getting back to the ecological fallacy problem, is saying just because people normally act like this doesn't mean there's not going to be some guy that wants to live out in his shack on an island, excluded from everybody. So we're talking about patterns here, and yes, there are, especially when we're talking about people that are making decisions for all sorts of reasons. We might not model all of their particular.
So you're saying that wildlife have patterns like that too? I know people.
Yeah, exactly. So I don't know everything about everything, but I do know that different species have a certain amount of area that they call their home range, right? I mean,
they got to be close to water. That's the reason water.
Well, those would be first order effects. Okay, so you're making the good connections here. So animals have to be close to water, and they have to have a food source, and there's everything that they need. They need to be close. Those are first order effects. Second order effects are how much space do I need separate from another species that's like me. So in other words, how far away are the two habitats from each other? So that if we look at the actual pattern of bear habitats on the Earth, maybe I'm just using bears as an example, how spaced apart are they? How close are they? Do bears tend to cluster, or do they tend to be patterned across the Earth because they need a certain amount? That's a second order effect.
Okay, while you're talking about that, I was reading an article, and since in Florida, since the inception of these python snakes in the area, they're eating up all the wildlife, and so all the natural wildlife that would normally be there, that would have certain things available for them, all of that is gone. And so now you get to repattern the environment based on invasive species that normally the first order effect would have been that the bear would have had food here, the deer would have, but they ate all the deer, all the bear, and so only certain species that live in there, and it has changed the whole pattern
Right.
you would think an animal would be, because they only run from the invasive species.
Well, some of the tools that we're going to talk about will help you come up with the measurements that would help you study those type of patterns. So, we've already talked about a bunch of tools that would allow you to study first order effects, right? Like we could. So let's say we wanted to study this first order effect that's given in this given in this example here, where we say as we travel away from water, or there's the soil type change. Let's just say it's soil type. So soil types, we can make a map of soil types. Let's say that we want to say soil type is related to tree species, right? What GIS tools could we use to establish that relationship? Let's say our soil types were polygons, and let's say that we had a tree species where every tree species was known. So we have a bunch of points, and those represent trees, and there's an attribute column that says tree species. How could we, and we wanted to answer that question. Is soil type, does it influence tree species? Well, I guess we shouldn't really say that. Does it influence? We'd have to find a biological reason for that. Like we'd have to study it more to see that. But the first thing we want to do is just establish a relationship. Is soil type related? In other words, does the spatial pattern that we see on the landscape, is it explained, or is it influenced by the spatial pattern of another variable? So how would we do that? Let's just say these represented polygons. We got one polygon here, we got another polygon here, that's this blue area, and another polygon here that represents this this dark green area. And we want to know, we want to find out if there's a relationship. What's something that we could do in our GIS system?
Could you, when they have certain trees associated with certain soil characteristics, so you can buffer any of that out, right? You buffer out a certain type of, if you knew the soil that was in that area, you would know only this type of tree can grow in there. It couldn't be a plan based on that. So
Maybe do spatial joining.
Yeah. So if our trees were all points, if we represented our trees as points, we could do a spatial join between these two layers that represented the soil type and the trees. And we could do a few different ways. One, we could do 3 different spatial joins. So we select out all of the maple trees and do a spatial join, and then we come up with a count of how many maple trees were in the green, how many maple trees were in the yellow, and how many maple trees were in the blue. And then do it again with oaks and willows. So we'd wind up with 3 counts. We'd have the amount of maples, the amount of oaks, and the amount of willows. And we could, at that point, we could probably do some sort of
Dissolve or?
Well, I was going to say categorical just by saying, oh, well, yes, there are way more maple trees in this area than that area. But there are statistical tests that we could perform that would help us to do that. We have a graduate level course in that. And actually, that's 715. That's being taught next semester. So we have a graduate in basically in taking the statistics and finding out, is it significant that there are, 5 trees in the green and 2 trees in the yellow and no maple trees in the blue? Could that have happened by chance? And that's a statistical test. Yeah, go ahead.
But see, you only seeing, so what we're talking about is without looking at the real world situation, and you're using the computer to model what is real world. So if that model that you have, you put everything in there, and you come out with the overlay of what it should look like, could you actually look on the ground and see if your picture is correct based on what you're assuming those joins will do? Those joins should match the real world aspect of what's really there. Wouldn't it do that if you just do all those different things and just put them in there and make a join?
I mean, are you asking, like, how do you know your data is correct?
Yeah, just based on this, see that picture that you got there.
Yeah.
Those spatial join, is there a spatial join you put together, or are you just making an assumption that all this should be like this?
Well, this isn't even real.
I understand that, but
Yeah.
if I wanted to know if what I'm saying is correct by doing a join, like what she was saying, and like you were saying, I'm gonna join all this together, and when I look at that final picture, it should look like, this picture should look like what I'm actually modeling on the ground, correct?
Right. So your data has to be accurate, right?
So, okay, so.
Yeah. I mean, if your data is accurate, the spatial join is going to be accurate, right? I mean, like, if your data is within 5 feet and you have one point that's within 5 feet of the line, you might have been wrong.
Okay.
But you might not have. Yep. All right. So that is an example of a method for doing for testing first order effect. We could also do an overlay, right? We could in spatial overlay. If we did an overlay, we would assign. If we did an overlay between these two layers, each of our tree points would get an attribute of the land cover polygon it was in, and we could then dissolve and do the feature count. So if we dissolved on the trees, we would get the same result as doing a spatial join. So that'd be another tool that we could use to study this this first order effect. Now, second order effects, we're going to talk a little bit more next time we meet next week about how to quantify second order effects. But today we're gonna do a few more first order effect principles today, and I'll actually demo some of them, and also quantify. We're also going to talk about quantifying spatial descriptive statistics, which we haven't done yet. But sometimes descriptive statistics are necessary. So, for example, an example of a descriptive statistic was, what if we wanted to find out the average location of all of the maple trees versus all of the oak trees versus all of the willow trees, and we wanted to plot where those were? That might give us a clue as to what the spatial pattern was too, right? So the average location of these, where would you expect it to be? Probably like about right here, maybe, I would think. The average location of all of these would be up here, and the average location of all of these would be like right here. Okay. So I know that you guys have probably calculated some of these, but we'll just bust that out here for a second. So so we talked about this concept of spatial autocorrelation. This is what we'll get into a lot more next week. But there's actually a way we can come up. There's more than one way. We'll talk about one way this week, and we'll build on it for next week. There's actually a way to come up with a number that will represent those different patterns, so that we could say, oh, this particular spatial pattern that exists on the landscape is very clustered. That's the top. That's A. Or this pattern is very dispersed. That's kind of like the central place theory I was describing. Negative spatial autocorrelation. Or really, there's no second order effects. These things just happen. Okay. And oftentimes you'll see that, like we did the tornadoes thing here, right? Now, if we did, one of the things about spatial autocorrelation or measuring it is that if we measure it at one scale, it might appear very clustered. Like if you guys know where tornadoes happen in this world, a lot of the tornadoes happen right here in the United States and the whole world. So if we did a worldwide map of where tornadoes occur, somebody looked at that, they might say that tornadoes are very clustered. However, if our study area was just Mississippi, it may be that there's no real second order effect. There's no real spatial autocorrelation going on. Tornadoes happen at random within our study area. So sometimes these patterns, actually a lot of times, these patterns do depend on what we consider our study area. And so we might not see a pattern at one scale, but we might see a pattern at another scale. And what that means, sorry, just a second. What that means is that the controlling process that's causing that pattern, so we talk about that a lot today, the process that's causing the pattern exists at that bigger, smaller, wider scale. Then it doesn't exist at that fine scale. In other words, there's no controlling process for that to occur. In other words, the thing that's causing tornadoes is a continental-wide thing. It's the fact that we got this Gulf of Mexico underneath with a huge area of relatively warm air, warm moist air, and the cool dry air coming down, and so this whole area gets tornadoes. But inside, there's not really anything controlling where they're happening inside that area. Yeah, go ahead.
I was just thinking about what you're saying is there could be a pattern. Is that a natural pattern, or like you said, sometimes it's hard to find our pattern unless you go out farther from the extent of stuff to see these.
Sometimes it's sometimes a pattern exists at a wider scale, a broader scale, and it doesn't exist up close. And sometimes it's the opposite, right? So yeah, that's it. Okay, so here, this is what I was referring to before. So if we see a spatial pattern on a landscape, we can theorize that it's the result of an underlying spatial process. That's what I was getting at. So the pattern of where tornadoes exist on the world, there's a process that creates tornadoes. Where do the tornadoes occur? If we see where, like I do a lot with coral reefs. Where do coral reefs exist? Well, they exist in warm climates with very clear water because they need the sun, because they have both a plant component and an animal component, usually that lives inside of every polyp, and so they need to have the light and they need to have the clear water, the warm water for the full animal to survive. So they exist at certain depths, and so there's a process that explains where they are. In fact, there could be more than one process or linked processes that explain where they get. Okay, so we kind of already explained what we did. I already explained what a first order property. So first order property, the ones I just listed with corals would also be examples of first order properties. So the corals need to be located where there's also other things. So if I had a map of those other things, I could predict. Okay, we've done this, but we've done this in this class before. We just haven't called those first order properties in this class yet. Yeah. The example here is taken from the book, the Oaks. Okay, so oftentimes we can do things like model a spatial process, okay, then if we model a spatial process, we can observe the result being a spatial pattern. Okay, so when we did capability suitability modeling, that's kind of what we're doing. We're coming up with different variables or different layers that represent first order relationships with the thing that we're trying to predict. sometimes, though, we don't directly measure the entity where it exists. We're trying to describe things about the particular spatial pattern, and that is referred to as descriptive statistics outside of GIS or outside of geography. But there are slightly modified ways to compute things. Like one of the descriptive statistics is the mean, the average. How do you calculate the average? Like if I wanted to calculate the average height of everybody in this room, I think I've done this example, but how would I do that? What's the formula?
And divide it by how many there is.
Exactly. Add them up and divide them by thing, every one of them. So if I have a bunch of points, so by the way, we call these things measures of centrography. Okay. So if I want to find out the average location of a bunch of points, I can compute what's called a mean center. The mean center, what I do is I add up all the x's and I add up all the y's, and then I divide each one of those numbers by the number of points. And then I get my average x and my average y. That's how I create a mean center. Okay. Mean center. So here I should open up ArcGIS. I'm going to use the same data that we were using before. Now, the example that I've given is with points, but we can also do this with polygons or lines. The math is a little bit more complicated, but not much. So we're just basically calculating the average all along a line or all within a polygon.
So I have a quick question.
Yes.
So the mean center isn't the mean point. It doesn't have to be on already existing point. It's a new point. Correct.
Right. In fact, now, yeah. So let me just show this because our GIS will actually calculate what you're talking about.
Oh.
So I'll just call this pattern 1 because we're going to do pattern 2 next week. So both of those tools exist in ArcGIS. You can calculate, in fact, a lot of these tools are grouped together in, let me add the database so that I can have it. So I'm just going to use the same data from the Tornado Lab, which was Lab 3. Those are my examples here. That's right. So I got all this data.
The 1971 you made yesterday or the old one?
The old one, the one from this class. That's the one I used. They're exact. Well, no, they're not exactly the same. The other ones don't have any of these other values. Okay, so I've got my I've got all these. First of all, let me show. In analysis, under tools, toolboxes, let me search for it. So I've got the mean center. So they're all in this spatial statistics toolbox. Just forgot. So in the spatial statistics toolbox, there's actually a ton, and we'll be doing some of these. Analyzing patterns will be next week. Mapping clusters will be next week. So this week we're mostly going to focus on this, and you can see that we have one called the mean center. The mean center is this one that I've talked about so far. Okay, but one that's not on this slide, but it's on the next slide, is the median center, and that identifies the location that minimizes overall Euclidean distance to all the features in the data set. So what does that definition kind of sound like?
Median center, you said?
Yeah, read that definition in your head. And does it sound like a concept that we already discussed?
Almost sounds like location allocation.
Exactly, and it is. So the definition of median center is the same as the location allocation, but the distance is not on the network. It's just straight line distance. So in other words, it's the feature that has the smallest average distance to all the other features. So if you take all the features and you find out what the average or total, it really doesn't matter, work out the same in mathematics. So it's actually the total. The smallest total difference to all the other features, that's the median center. So it is a feature that you're already using. Okay. All right. So for example, let's go back here. Just so that it'll run fast. There's not a whole lot of Major League Baseball teams in the United States, right? Tonight's an exciting night for me because I grew up till I was 12. I lived in St. Louis, and then I moved to Los Angeles area. So they're both in a Game 5 winner-take-all game tonight, right? Cardinals and the Dodgers. I don't know. So I got a 50-50 chance at least one of my teams goes on, right? Well, not a 50-50, but I think the Dodgers, they'll pull it out.
They'll win.
The Cardinals, I'm not so sure about. All right. Okay, so let's do an example here real quick. So we've got our mean center for all the baseball teams in the United States. Where is the mean center of baseball teams? So attribute table. What's that?
I think probably in Illinois, all the customers, East Coast.
Bet in Kansas.
All right. This is all all of the baseball teams, and the weight field. The weight I was looking. That's why I was looking in the attribute table. So what the weight field does is instead of this formula right here, it will actually what it'll do. Sorry, I like pointing things out up there, but that's the way it gets on the video. So what the weight field will do is each of the observations will be multiplied by the weight, and then the weights will be included. So the sum of the weight will be the denominator. So in other words, if you have right now, I don't think there's any Major League Baseball teams that share a stadium. I don't think there are. But if you were doing this for NFL stadiums, we could weight the. Oh wait, do the Jets still share? I don't know. But at one point, the Jets and the Giants shared, right?
They still do.
They still do. Okay, so you could weight that stadium in New Jersey double, and what that would do is double count that particular stadium.
Maybe two teams.
Yep. So actually, we'll run an example of this that'll make more sense here in a second. The case field, this will allow you to determine where the central feature is, and it'll return a central feature for every case. So let's just run it without any of these for now. Run it. Okay. So the result here is right there. So that's the average location. So if we average all the x's and all the y's, just by default we get that. What's that?
I said I was close. It's close to Illinois, right?
Yeah, you're close. So have you guys ever seen something like average center of U.S. Probably seen this map. Population over time. Right? You've probably seen a map like this.
Shifting more west.
Right. So you'd have to go back in the census and get the census data for because the census happens every 10 years. You have to go back and you could if you put the census data in the GIS, I'm sure, the GIS didn't exist in 1790. I know for sure. At some point here, we'll get data, but I'm sure you could find it somewhere. I know you can get GIS data, all the way back to like 1950 for sure. So you would do the same thing, but you'd calculate the central feature and you'd weight it by the population because you probably could get county level data at the best back there, right? Like it's even if you got the actual census and you read the census and it had an address, it'd be really hard to map all those, right? Okay.
If they even existed, like back in college.
So that was based on the population is moving across the United States.
Right. So this is the central. This is the mean center here. The mean center here. The mean center. I calculate it over and over and over again for all those data. So I don't actually have in this U.S. counties data. There's no population field, but there is for these large cities, I think.
Wow.
That should be a table. See if there's a See, there's a population in 2016 and 2017. So we could put the large cities in here and use call this 2016. And this time, I'm going to go P 2016. This time I'm going to use a weight field. I'm going to use the population in 2016. So what that means is that it's going to weight each city by its population. And if I run this is just the population of large cities. So the population of large cities, the mean center is right there. The population of the baseball team average location's right there. Okay.
Is that why they chose, or they made Dorothy come from Kansas, like back in the day?
Yeah, maybe so.
Represent the center of the country or something.
Yep.
Somebody like political voting on it.
Yeah, something like that.
So if I run this again, 2010, let's see how different it is. So what would this tell you?
Yeah,
More people moved to the southwest.
Yeah, so this is 2010, and this is 2016. So I mean, that may not be significant. That may not seem significant, but that took a lot of people to move in this direction to get that center to go that way just a little bit.
Phoenix is blowing up.
Right, Phoenix is a growing city. You know, we could create another map that just showed population change, but you know, this might be an interesting statistic to report, even if we didn't map it. That the mean center of the United States moved, you know, however many, feet or meters or miles, right? So we just made a small version of this map that I was trying to show you. Okay. Yep. All right, so that's the mean center. So we could do that. Like, this is a socioeconomic thing that's associated with this, but we could go back to our course. Where's the? Yeah, it's right here. Oh, I got rid of it. We go back here and find the mean center of each of these three. That's what I'm trying to talk about. What's that?
How would first order and second order affect? You know, it's like a pattern it's a natural pattern that we seem to be doing.
Well, this is just one tool for looking at. This is spatial descriptive statistics. So this is we're not necessarily yet looking at pattern, but we're kind of trying to describe the pattern. And so this is the beginnings of second order spatial effects, because we're looking at how they're affecting each other. Okay, it's like how the pattern of people, how they're affecting each other. Technically, second order spatial statistics would be at looking at the pattern. Is it clustered? Is it dispersed? Is it clustered in some areas and dispersed in another? If I took off the yellow pattern here, look at this area right here. Like I said, the Great Plains of the United States.
Right.
Cities, large cities, tend to be kind of spaced out in almost, I wouldn't really call them regularly spaced intervals, but there's a pattern associated with them. Whereas, you know, here in the Intermountain West, cities almost appear to be random locations. And then the rest of the United States, particularly the East Coast and California, where you get a lot more people, the large cities are very clustered.
Does the environment have effect? Is it?
Yeah, I mean,
the people in what people do?
Right. So those are the types of questions that you could answer. Like, you know, I'm not necessarily a social scientist, but if you wanted to study that, you could say, first of all, you could next week when we get to this, you could quantify and determine if the spatial pattern changes. You could say in this area it's dispersed, in this area it's random, in this area it's highly clustered, and then you could divide it up. You could say coastal areas are characterized by clustered patterns, and you have a number to back that up. It's not just an observation like that you see. You say, these areas, and then you could compare that to China and say, in these areas, they're also clustered, or they're not clustered for some reason. You have a number to back it up to say these areas are way more clustered than these areas. Is it cultural? Is it?
In the 331, they had where they had almost 4,800 patients per square mile in India, and in Denmark it was like 0.2
Yeah.
people. And what causes that? I guess it's because of I can say that all these people live in one area, so they crops and live there, or leave there, or whatever. But the environment doesn't have anything to do with it. I guess it's people that governments do have.
Right. I guess what I'm trying to say is this class isn't necessarily about explaining all the whys that exist. It's about giving you the tools to help you analyze the whys. Right. All right. So that's that. If I go back to Major League points, and I do want to show you what these other things mean. So I'm just going to overwrite the mean center here, and I choose not to have a weight field, but if I choose to have a case field as the league. So baseball is divided into two leagues: the American League and the National League, and I don't really know if that will have any effect on the patterns that exist, but let's see if the center of the average of all the American League teams is different than the National League team. So that's what this is doing. So you can set a case field, and that case field will give you two central features. If you have two different values in the case field, you have two values, and we do, American and National. Now, if we did this with this, and we set a case field for the tree type, how many features would we get in the output? Three, exactly. We get three different features, and they would be the center of the oaks, the center of the maples, and the center of the willows. So that's what that does.
And the reason why you didn't weight them this time is you just want to see the pattern.
I don't have a field to really weight them by. If I had the populations, I could do that, or how much money they spent, I could weight it by that. I don't.
So the real reason why you will weight it is you want everyone to have the same added weight. Maybe whatever particular number is. By that, they can move at the same pattern without being unweighted. Unweighted, you don't know the reason why they're.
Well, unweighted, I'm counting every single point as one. If they're weighted, I'm counting the points. I'm counting points that, whatever the weight value is, I'm counting it as that many points.
Oh, okay.
So with population, I'm counting the bigger cities more than I'm counting the little cities.
Okay.
And so the point will move closer to a bigger city than it will move closer to a smaller city. So here, if I go to symbology, I don't know which one of these is which. If I say unique values and league. So it's hard to see, but the average American League team is right there, and the average National League team is right there. This might be old data, because Houston did switch, right? Large cities. Nope. So they're still no. That said national, didn't it? Houston's now in the American League, so that one got counted wrong. But before a few years ago, this would represent that on average, the American League teams tend to be more clustered in the Northeast than the National League teams, which tend to be more dispersed throughout the United States. Is the way you could say that. Yeah, here I'll show you to answer your question a little bit. So here's large cities, and I'll call this P un 2010, and I will not do a weight field. So this is the unweighted population here. Thank you. The unweighted population in red and the weighted population in green. And so if we just take a large city at its face value, the population would be a little bit further west. Why? Well, what that means is that there are bigger cities in the east that are pulling it more towards that way than the cities out west.
Okay.
Because we're weighting all cities equally on the red one, and we're weighting cities by population in the green one.
So you weigh them by locations as large big cities versus population?
Well, just the nature of the formula is the average x and the average y. So that's the spatial component, and the weights determine. We multiply every one by its weight and then divide by the sum of the weights instead of just by the sum. It'd be like, okay, so if I said this test counts twice as much as the first test, if I said the final counts twice as much as the first test, what I would do is take your 2 grades, I'd multiply your final by 2, and then I would add those together, and then I would divide by 3, because I'd have 2 finals, doubling the final, and 1 regular test. That's the sum of the weight part. All right. Okay, so the next step would be to look at the. We never did central feature, so just show you how that's different, or the mean center. ArcGIS actually has this this one called the most centrally located feature in a point, line, or polygon feature class. And the median center is the one that minimizes the overall distance. You might think those are pretty similar definitions, right? Like, how does this one work? Well, it might be best to read it. The smallest accumulated distance to all other features in the data set is the most centrally located feature. Accumulated distance, Euclidean distance, Manhattan distance, or as specified by the distance feature. So it sounds pretty similar, actually, except for you can specify what the difference is. Yep. Okay. All right, so if we do the Major League Baseball points and we just press go, then it will tell us what the most centrally located Major League Baseball team is, and it looks like it's median feature. Okay, so I was a little bit wrong. A lot wrong, sorry. Not a lot wrong, but the median center is the location that minimizes the distance to all features. It doesn't actually have to be one of the features. Okay. Central feature is the one that was most like location allocation, and that's how I was wrong. Yeah.
So you're saying that the one in yellow is central location of.
That's the median center. In other words, that location minimizes the distance to all these other locations.
Okay.
Right. So it's different than taking the average x and the average y.
So it would be like a distribution center.
Yeah, it would be like a distribution center for an airplane, because we're not necessarily concerned about the path, because exactly. It's Euclidean distance.
So the only one that has to actually be a feature is central feature. So it's actually one of your points.
That'll be one of our points. Okay. So it'll probably pick one of the Chicago teams. Let's see. Central feature.
Okay.
Yep.
When the nearest two, can you use the nearest two to do the same thing?
White Sox. What's that?
Could you use
White
the
Sox
nearest,
is American.
nearest two to do that?
You coordinate major.
A nearest two, you know that nearest two,
Yeah.
can that be used for that? Or
Well,
that's-
the near tool will actually. It's kind of interesting you said it. So the near tool will find the closest feature in another data set. So the near tool, if we ran it, you have to feed it 2 data sets. So you feed it one data set. So we could say like we could have rivers, and we could find out. We could feed it the Major League Baseball teams and find out the closest distance to a river for every baseball team. That's the way we could do that. We could actually do this. Did I already say this?
Or airport?
So if we let's say we had the water, and we were concerned about the first order effect of the water, we could say, what is the average distance? I'm sorry, not what's the average. What's the distance to water for all these trees? We could use the near tool, and we'd wind up with a column that had the distance to every tree from water. That's what the near tool would do. And then we could actually do a dissolve. Did I already say? I feel like I already said this. We could do a dissolve on the tree type and get the average distance to water for each tree type. So we'd run the near tool and then a dissolve, and we would get the average distance to water for each tree type, and then we could find out if that was significant. We could say, oh well, the average distance to water for willows is 5 meters. The average distance to maples is 20 meters, and the average distance to oak trees to water is 22 meters, something like that. But that would involve running the near tool and then running the dissolve.
Dissolve.
Yeah. Sorry, did somebody else have a question?
Would that go to the center of the lake, or would that go to like the edge of the lake?
Near does the edge of the feature.
Okay.
The closest point too. So what would be possible for this one?
The closest right across.
It'd be this distance and that distance. It'd be possible for those distances to be very similar.
Okay. Yeah.
So it's the closest. The near tool works by doing the closest feature.
So would you use that to just look at the observation of second order effect? Would it be another tool to bring about an understanding about the first and second order effect?
Well, you would probably need to use Python or something to study the second order effects. Because remember, second order effects are about being baseball teams. Are they close to other baseball teams, or do they happen to be further apart than others? It's the distribution of baseball teams. In other words, it's how baseball teams affect. I keep saying baseball teams, but it's how anything affects another one of that thing's spatial position.
Like airports. Every team by an airport.
That's a first order effect.
Oh,
Yes.
like,
Second order effects are how.
Airports are over 50 miles.
Yeah, how airports aren't, you don't get 2 international airports right next to each other. It rarely happens. Like, there's a big airport in Chicago, O'Hare, and there's a kind of Midway, which has, some Southwest flights, but it's not the biggest airport ever.
So would there be a
But there's no big international airports right down the road from each other.
Yeah, they're in like Dallas.
Like Dallas has one major airport. It also has Love Field, but it doesn't have another, even though it could probably support another one. But everybody just puts the money into the big one that exists. See what I'm saying?
So there's no major league team without an airport. All of them gotta have an airport.
Okay, but that's a first order effect.
First, okay, but what would be the second?
So
effect?
a second order effect is that, well, for example, you know that when the Expos moved to Washington, the owner of the Orioles put up a big stink. I don't want a team that close, right? So that is an example of a second order effect. Baseball teams can't be too close together because it takes a large population base. I got 80 home games every year, and you got to fill up a stadium of 40,000 people. And so they can't be right next to each other because they compete too much There's a reason why there's not 2 teams in St. Louis anymore since the 30s. The Browns moved to Baltimore, and that's because of the second order effect. As the population grew and St. Louis became a relatively small town, it could no longer support 2 baseball teams. So it's a second order effect. The effect of having the Cardinals and the Browns in the same town, their effect of being too close together, that's the second order effect.
Okay.
And the spatial pattern that results is that we don't have, in most of the time, 2 baseball teams that are that close to each other because they compete too much with each other.
Yeah,
Unless it's a really big town like New
I
York.
think what you're talking about is the LA. Who's the team that they just were the best team for the last 5 years? It was a baseball team.
Basketball team?
Yeah, what was the team that always? Who? Yeah, Golden State. Golden State just had a stadium built in San Francisco. They were using LA, and because of the very thing you're saying, you got 2 major teams in one place, and they cancel out each other. And so, in order to
A second order effect is anything. It could be a sports franchise, could be an example in nature, but it's the competition or the utility to cluster. The competition that causes dispersion or the utility, the benefit of clustering. Like things are clustered. Like, why do you think shopping centers and malls exist? It's because people want to just go to one location and get a few different things, right?
Like hospital parks. You have like your radiologists and you have your
Medical
center.
facilities.
Yeah,
You have them all,
here.
so you don't have to drive all over town to go to the other.
Yeah.
You show up. Oh, you gotta get an X-ray. That's 10 miles away. It's like right next to it.
well, but I think they decentralize malls now. Malls are going away, and they act like they're doing the opposite of it. Now, it used to be that's what you were saying. Breaking them up into.
Yeah, and there's a process that's involved in that. I don't understand all of the processes that are involved in people's shopping habits, but you're right. Spatial processes change over time, and they result in having different spatial patterns or changing the spatial patterns in the landscape. Yep, exactly.
So what? Which creates a pattern that can be studied.
All right, so let's go back to population for a second. That's large cities. That's the only thing I have population for. And I'm going to do population 2010. I'm going to do S, population 2010. And this time I'm going to do, the central feature. I'm going to go back to, directional distribution. Okay. What directional distribution does is it gives me it's this one, a measure of the variance between the average distances of the feature to the mean center. See this circle here? Okay, so it kind of gives me an idea of how dispersed a particular entity is. So here I've got my population, my large cities. I'm going to call this 2010 and do this for the 2010. And the ellipse size will be 1 standard deviation. So it's going to run, and what I'm going to get is this circle represents 1 standard deviation away from the mean center, which I think is still this yellow, the green one. Okay. So that tells me an idea of how they're dispersed. Okay, and I can look at how this changes over time. So let's see what it looks like in 2016. It probably won't look too much different, but I can see I can actually see the difference in the area. So let's make them a different color. So the 2016 will be red. Okay, they almost look identical. So let's zoom down in here. So again, it looks like it's just showing us the shift in the south and the west direction. See how when I get almost due north, now they're almost the same line again. So in other words, the population didn't change much north to south. It mostly shifted east to west. And if I go west, You can see that change.
So you have a great shift to
There is a pretty good shift to the south, southeast, but not a very good shift to the north and the northeast. In fact, the shift is the opposite direction there than it is down here. So that's that's actually this one, the standard deviational ellipse. So I think you can do both of them. Standard distance. Standard distance, RGI is called the standard distance. That's this one, where it's just giving you a circle rather than an ellipse. So it's not considering x and y separately. This one creates the spread in x and the spread in y, and this creates just the spread in just the spread of all the points in general. So you get a circle. So this will tell you more about the direction, and this will tell you a little bit about the direction, but the circle will just be shifted. So this one's a little bit more about looking at the size of the circle and seeing if it's getting more spread out or less spread out over time.
So that's the standard distance, more about the size of the circle, not the direction.
Right. Yeah, I mean the circle itself will still be shifted, but you won't be able to tell those north, south, east, west type of things because it's just a circle that's moved. All right. Oh, and now that we're starting to do these statistics, it's a good time to bring this up that these statistics require your data to be projected. It can't be latitude and longitude data because latitude and longitude doesn't have this concept of, I mean, you could still stick the numbers in that represent latitude and longitude, but the math doesn't really apply because a difference in latitude of 1 degree and the difference of longitude in 1 degree is a different distance, and it changes depending on where in the globe you are. So when you calculate these things, make sure you're using projected data. So I am using projected data here, but yeah, make sure you do it. Okay, so central feature is that one that's like location allocation. Standard distance is so the difference between central feature and mean center basically is that central feature is going to choose one of your existing features, and mean center is choosing any possible location that minimizes that distance. So those are the differences between those two. Mean center is just the average x and the average y, and you can weight any of these actually, and you can also assign a case field to any of those. So the case field will come up with n number of features depending on n unique values in the case field. All right, so standard distance is that one that measures.
is not directional.
Yeah, so I should actually have both standard distance and directional distribution, which are both of these on this slide. They both measure spread, but one shows you more about the direction of the spread. Okay, so now we're gonna talk about something we've already done, kind of, but talk about why it's important in this concept, in this framework of statistics. So we're going to talk about measuring density. This is something that's often done. In fact, there was a question on a test that measured density of traffic accidents in wards of a city. That's local density. So we're measuring density based on some other feature. We can also calculate the global density of a study area, and sometimes it's interesting to compare the global density of something occurring to the local density of something occurring. So we could say, globally, when I say global, I don't mean all over the world. I mean all over an entire study area. So we could say, in the United States, the density of tornadoes is 5 every 20,000 kilometers per year. But in Missouri, we see 50 every 20,000 years. You see how that might be, 50 in every 20,000 square mile area. See how that might be provide an additional set of information that would be useful to the user to compare it to an overall statistic. And so measuring global density it's pretty easy. The only problematic is how do you measure this A at the bottom? So here we've got our statistic, which is the number per area. Okay. So if we wanted to say that the United States is our quote-unquote area, then how would we do this? How do we actually implement this in the United States? So we have a polygon that represents the United States, and we could calculate the number per area.
Then the total area.
Yeah, we could do this a lot of different ways. I mean, if our tornadoes data set was already limited to the United States, we could just count up the ones that we wanted to apply to the global.
Like the amount of tornadoes or the
Yeah.
area of the U.S.?
Right. Well, both.
Okay.
So you can use
The
that,
numerator is the number of tornadoes. The denominator is the area.
so you can use that chart for global and local. And so we get the global and pick one of the area.
Right.
And then you do a local, the local area will be that part with the equal sign and then the number in that area.
Yeah. So my point is there's no like global density button, but this gets done the same way we've done other things. So we could do it with a spatial join. You could do it with an intersect, but you need the numerator is the number of observations in an area, and the denominator is the area of that area. So that's calculating density-based analysis. So lots of times we do density-based analysis. We can measure a point's pattern density using this concept, and there are two different ways to do this. One we've already done, which is the quadrant density. I'm going to skip to that one. Well, no, I'll talk about kernel density. So kernel density is something that we actually cover in the other GIS class, spatial analysis. And spatial analysis, kernel density takes a set of features and it creates a raster data set. So what it does is for every raster cell, it counts up how many observations they are within a certain distance of that raster cell. And then it takes the area of that search radius and assigns it to that raster cell. Okay. So we're not actually going to cover kernel density in this course. We cover it in the other course, but it is a tool. It requires a spatial analysis license, and it's very similar to quadrant density, except for the number of features will be overlapping. It'd be kind of like if we did our remember when we did the tornado lab? It'd be like if we did the tornado lab, but for every single value we said within a distance of, and we went way out beyond. And so every feature would get all the features within 1,000 kilometers of every. I'm struggling because I want to say quadrant, which is what I'm going to call it in a second. But every hexagon. Okay. Every hexagon. All right, that's different than quadrant density. Quadrant density is what we did. We calculated this. I also said this at the bottom of here, but quadrant density is something that's done a lot in spatial analysis, and that is that we calculate the number of observations into subregions. Quadrants, though, are typically different than all of the things that we've done before, in that they're typically the same size. So we could say what's the average number of tornadoes per county, right? And that's kind of like quadrant density. The problem is counties are different sizes. Remember, we pointed that out when I brought that up, is that it'll give us a problem because some big county will just get a higher value just because it's a bigger county. We can do things to solve that, like divide by the area of the county. But a better way is to just make all the quadrants the same size. They can be different shapes. Lots of times they're hexagons. The second most common shape for a quadrant is a rectangle. Probably why they're called quadrats. What's that?
Triangle, hexagon.
They can also be triangles. We could.
Can you do that for cell tower? It could be any item that you turn it be.
Cell towers.
Can you do a dent in the area?
Well, you could use cell towers. Like what do you mean by
Well,
dense?
this is how many cell towers in a particular given space. Because they got them all over. You know, they're not in every place, but they are fixed. You can tell back in Harrison County how many cell towers up there, big things. It might be thousands, and here you go up north, it might be like 10 or 11. So,
What are you trying? What's the question you're trying to
the
answer?
whole point is you can do a density on any object.
Yeah.
As long as you know what it is.
So you could make a map of cell tower density. Yep. Is that what you're asking? So if I created a bunch of hexagon tessellation if I had all the cell towers mapped, and I had hexagon tessellation of the United States, I could do a spatial join and make a map of cell tower density. Yep. I could also run kernel density analysis, and it would do a similar thing. It would. Here, I'm just going to run this because might be good. So here's kernel density. So I can say I'm going to actually choose the tornadoes, databases, pattern. Nope. Databases, lab 3, tornadoes, and I'm gonna make my cell size some nice round number, 10,000. My search radius is how far out I want to look. So in other words, what it's going to do for each cell, it's going to find out how many tornadoes were within 100 meters, because that's in meters of that cell. So the area units, yeah, that's fine. Output densities. Run this guy. This might take a little while, but I'll come back to it. So this is gonna create a raster data set. Okay. So we normally implement doing quadrant density as either a spatial join, more common, or a intersect or overlay. And you can create quadrants in ArcGIS. I don't know what's wrong with this. Okay, I didn't create a big enough. There were areas where there weren't any tornadoes, I guess. Search radius. Run that again. Yeah. So you can create search radius. It's not. Did I make it too big?
Really small.
Anyway, I'm not exactly sure why that's not running, but what I'll do here is.
Did you have 10,000 instead of 1,000?
Yeah. Well, we're not. This course isn't really focused on that, but I'm just gonna show you an example output here. Oh, that doesn't have an example output. Here we go. So here is a kernel density map of heart disease. So you see how it's a raster. It's a smooth surface, and what it's doing is it went through each cell and it searched an area around that cell, and so you get a higher value if there was more heart disease within a certain distance of that cell. And so it's a way to show a cluster where a cluster is occurring. It's one way. We're going to talk about some other clusters soon, but we're stepping closer to measures, second order measures. So this is showing where things cluster and where things are lower. Okay, where they're more dispersed. It's not actually making a determination as to whether they're dispersed randomly or dispersed in a pattern, but it is showing. Yeah, it's a descriptive way of showing the pattern that exists. So that's kernel density. So if you want to create quadrants, going back to what we were talking about. Generate tessellation. So we can generate all sorts of different tessellations for that are possible. We did hexagons already. I'm going to say current display extent, and we could choose triangles because you were asking about triangles. Run this guy. And now I have a tessellation of triangles. See that? So I could use these as quadrants. I could find out, what's the density of tornadoes in those quadrants. Hexagons is by far the most common one used, and that's because it's the closest shape to a circle that can tessellate. A circle can't tessellate. There would be spaces, right? If I did circles. But I could do diamonds, which are also known as squares that are tilted, and then transverse hexagons, which I think are just tilted hexagons. There are other things, and there are sets of shapes that will tessellate. If you've ever seen a soccer ball, octagon, not every soccer ball is like this, but octagons and squares will tessellate. But that gets to features that aren't all the same. So typically you want them all to be the same, or it kind of defeats the purpose of doing a tessellation. So they don't have to be all the same. Like we could use counties, but if we do use counties, it's important to where are these things? If we do use counties, it's important to normalize by the area, just a divide by the area. Okay. All right, so when I said how we calculate this, hint, we've already done this in class, that's spatial join. The reason that we do spatial join, one of the reasons we do spatial join is to do quadrant density analysis. All right, so this might be something that we would do is we could take different elevation regions. So this is the example getting back to the beginning of class. We could say, what are the average width of trees in low-lying areas versus higher areas, for example. And what we could do is come up with a polygon that has the different elevation regions, one being low elevations, medium elevations, high elevations, and the very highest elevations. And then we can measure things like point density or the width of trees, lots of different things. That would be covariance in density. One example of this is that we basically looked at, this was an article that we published a couple years back, and we looked at the damage that was occurring in areas. So actually, I'm just going to pull up this article because it's better. All right, so this is a research article. All right. So we're in the Florida Keys here, and Florida Keys is affected by hurricanes. That's what this is showing, right? All sorts of hurricanes coming into the Florida Keys. And the Florida Keys have they have vegetation growing on them, of which a large portion of that is just pine trees, kind of like here, but for different species of pine trees. But the elevation, has anybody been to the Florida Keys before? Okay, the elevation doesn't change much. They're mostly flat, but the elevation changes a little bit. We're talking about micro changes in elevation, though. From I think 5 meters is the highest above sea level. So here, what we did was we took two different images. This was in 2001 and then 2011, and we calculated the NDVI. And that is a raster data set. So actually, I do this as a lab in my raster analysis class. But those observations could have been points. I mean, a raster data set is just a bunch of locations in a raster cell. But let's say they were points, and we could calculate the number of trees that died or changed versus the number of trees that stayed around, based on elevation. So we can make one polygon representing the very low elevations, one representing the medium elevations, and one representing the very highest elevations, and calculate the number of changes. So that's what this chart is showing here. Okay. So here we've got low elevations, medium elevations, and high elevations. And then this is two different islands, Big Pine Key and No Name Key. And this is the change that occurred. So we calculated it based on pixels. So, there are ways to do these same things in a raster environment. But if these represented points, we'd just take the average number that changed and the average number that didn't change, and we come up with the ones that changed. Okay. So looking at low, there was more change than in the high elevation areas. In other words, everything that was above, these were in feet, and so he converted them all. But so basically, from 1 foot, everything above 1 foot was very little change, and anything below was a 0.3. So that's almost right on to a half a meter below the sea level mark. That doesn't necessarily mean that it was below sea level. It was below the datum. So anyway, in the low elevation areas, the presence of the hurricane had more effect, and we actually used a test that we'll talk about in 715 called the ANOVA test to see if this was significant. Okay, because those look pretty similar. Okay, there was a 0.19 change versus 0.16 versus 0.14, so there was a greater degree of change. So in other words, almost 20% versus about 15% versus a little less than 15% of the pixels or points changed over time. But this is basically, we could have done this doing a spatial join where the polygons represented the low, medium, and high elevations, and we calculated the change that occurred there at those points. All right. So this gets a little bit into next week. What we're going to start talking about next time we meet, second order properties. And so second order properties involve calculating the distance between neighboring observations. And so, Elvis, you actually asked that question before, and I think maybe I got distracted or didn't quite finish answering it. But you were asking, can we calculate the distance from every Major League Baseball stadium to the next the next closest Major League Baseball team using the near tool? Maybe I did answer it because I remember thinking it. You could do it with a script, right? So you could select out just one feature and then run the near tool and figure out how it was closest to all the others. Okay? But that's actually what the tools that we'll talk about next week do. Okay? So the first thing they do is create that table that looks like that. So this table is what you were talking about. If these were all the Major League Baseball teams, this table is the from to distances from every observation to, you could actually do it to the closest observation, or you could do it to all the other observations. This is just to the closest observation, right? So 1 and 9 are the closest. That's the distance. 2 and 10. So that's, I don't know where 10 is. 2, 10. I guess that's the closest one. So these are all those pairs, those point pairs. And that's actually the first step in most spatial autocorrelations. So we could come up with the average distance to every other feature. Okay. That's what this is. The average nearest neighbor is one of the first statistics that we're going to talk about, or today we're going to talk about it. The average nearest neighbor tool measures the distance between each feature and its nearest neighbor. And we come up with a number that tells us that. And so we're forming the basis for looking at pattern. Because we could calculate this on two different things. Like we could calculate this on the American League teams versus National League teams and find out which ones tended to be more dispersed than the other. Or we could calculate on tornadoes in one year versus the next year. I don't know why that would change year to year. Can't think of a process. Well, we could do it on this. This one, we'll go back to here. Did I get out of it? There. Go back to here. We could calculate whether maple trees were closer together on average, or oak trees or willow trees were closer together on average. Okay. So I don't have that data, but we could pretend that the Major League Baseball teams are that, and we can run it real quick. Oh, I didn't mean to close that. And after this, we'll take a break. The average nearest neighbor tool is also in the spatial statistics, but it's in a different toolbox. It's in the beginning of this analyzing patterns toolbox, and we'll talk about the rest of these tools next week. Average nearest neighbor, if we select the Major League Baseball points, do Euclidean distance, we could run it. Oh, I want to generate a report. Okay. Most of these other tools that are in the analyzing patterns and the other toolboxes, they generate a report along with the result. So what you get here is the result that shows you the average distance right here, 259,370. This tool doesn't return any spatial thing. There's no spatial result. It's returning you a number that shows you the observed mean distance, and then the expected mean distance is if we had the same number of points and they were in the same area covered by this, we would expect them to be this far apart if they were just randomly placed on the Earth. Right. So that's the expected mean distance. They're pretty similar. Okay. So let's look at this report because it'll tell us a little bit more about that other information. So we'll explain this a little bit more next week when we look at the other observations. But what this is telling you, if you look at the report, is that Major League Baseball teams are more likely random, at least at this scale, than they are dispersed.
Right.
And what does that mean? What's the difference between random and dispersed?
Well,
Dispersed means they have a kind of a pattern and they're spread out, and random just means it's anywhere.
Right. Random just means they're anywhere. Dispersed means that they're spread out in an evenly spaced pattern. Okay. And clustered means that they're grouped together.
Right.
So using the average nearest neighbor, which only looks at the distances and actually has a little bit dependency on the area itself that you're studying. So some of the other measurements that we'll build on are better. It's saying that it's more of a random pattern. In other words, the location of a Major League Baseball team doesn't really affect the locations of other Major League Baseball teams. They're just kind of spread out. And that may be true to a degree, but we know it's not completely true, right? Because I talked about Baltimore and Washington earlier that they have that area. It could be only in certain areas that they would be dispersed. It could be that there's some other first order effect that is just so much more powerfully explaining where baseball teams are than the second order effect, which is the pattern. Okay, what first order effect is going to really drive where baseball teams are?
Population.
People, yeah. So Major League Baseball teams need to co-locate with people, and so that pattern is just more relevant than this pattern. And so, we got New York and Baltimore. I mean, in Boston, they're all close together up there, but there's a lot of people, so they can survive. Plus, there's the whole historical aspect, right? Like, teams have been in certain areas for a very long time, and there is a cost associated with moving. I mean, although it does happen. So let's look. See, let me change this a little bit.
So what would you find on? Well, cluster is almost like a known pattern, but when it's random, it's best to run a near tool on a random just to see why it is that it is what it is. Why would you want to run a nearest tool?
Well, the near tool is for looking at first order relationships.
Okay.
So it's not really for looking like
You want to do it on first, like if it's second and first.
Well, it's yeah. Let's look at this. So if I take my Major League Baseball points and I put my near feature as my Major League Baseball points, and I run this guy, then where's it going to put it? Oh yeah, it puts it in there. Okay, so I open up my Major League Baseball points, which are right here, and I go over here. So actually, it worked differently than I expected it to work. So I expected this to be 0 because the near FID should be the same one. So it looks like it's smart enough. The near tool is smart enough to find the next nearest team. So the next nearest team 6. What is 6? So the nearest team to the Los Angeles. To the Anaheim, the Los Angeles Angels, which they're not even in Los Angeles. The nearest team to Los Angeles Angels is the Los Angeles Dodgers. Okay. And the distance between those two is this distance. See that?
Almost like the same.
So we can actually use the near tool to calculate the average nearest neighbor. So what would I do to get that value? How can I calculate the average nearest neighbor value now that I have this number? So did everybody understand what near distance did? So I expected near, because I put in the Major League points both for the input features and the near features. So I expected to say, okay, well, the closest team to the Los Angeles Dodgers is the Los Angeles Dodgers, and the closest team to the Anaheim Angels is the Anaheim Angels, and the closest team to the St. Louis Cardinals is the St. Louis Cardinals. But it's not what it did. What it did was it recognized that I was inputting the same thing in both, and it actually found what the real nearest neighbor was, right? So now I have all these distances to the real nearest neighbor. So going back to the slide here, going back to this slide, the average nearest neighbor measures the distance between each feature and its nearest neighbor. So I have that. I have the average feature. I have the distance between each feature and its nearest neighbor. How do I get the average distance between each feature and its nearest? Yeah, or there's that's exactly right. That's how I do it. But I can also just right-click here and say statistics. Or not statistics. Summarize. Statistics is interesting. Summarize. and I just get the near dist. I want the mean, and I don't need a case field. Run that guy. I'm not going to get a table out of this. So 259370. Let's go back to the history and see if that's the same number, because it should be. I mean, they're defined as the same. 259370. It's even like down to the millionths. It's the same number. See this number right here? This number right here in the table, the one that says average nearest neighbor, observed mean distance, that's the same. Now you don't get the rest of the report, but I'm just showing you mechanically how they calculated, how they created that. They found the distance of every observation to its nearest neighbor and came up with that number.
And the neighbor would be one team against another, his nearest neighbor.
Yeah, it'd be the distance from every team to its nearest team. So you can't, basically, I was telling you, well, the near tool doesn't really give you the information that you want, because I thought all these would be zeros, but it does. And so you can use the average nearest neighbor. You can use the near tool to calculate average nearest neighbor, is what I was demonstrating. Is what I just showed.
Would it be a more accurate?
No, it's the exact same number.
Exact same number.
Yeah, in fact, the nearest neighbor tool created that report, which is valuable. Okay, because this is showing you that. All right. So the last thing that I wanted to do is select. Okay, sorry. Go ahead.
One more quick question. So the number that it came up with for the average nearest neighbor, that's the average distance between the two nearest baseball
Yes.
stadiums.
The average distance between any two
Yeah.
nearest, the two teams that are closest together.
To each other. Okay.
Okay, got it.
Yep. So the closest team to Denver is probably, well, we can find that out of the table.
Well, you wouldn't know until it come up and tell you which one it is.
Yeah, but the closest team to Denver is probably either Arizona or Texas.
Might be that one in Missouri too.
You're right. It could be Kansas City. And it's probably Kansas City. So anyway, yeah, you can find that out on the table. So that's one of the things that the near tool can tell you that the other one can't, is that it can tell you that the other one can is the pairs, which one's closest to which one. It's kind of like that origin cost distance.
Well, those two pairs, look on the East Coast, and you was in Pittsburgh and Washington. Now, which one they do compare?
Well, I know that's the closest teams. So if I open up the near,
Well, you can see it.
where is the near?
So we got three of them in the same area.
Did I run? Oh, the near tool. The near tool just is in the Major League Baseball points. Okay, so if I actually sort this by near distance, and I look at the very, very smallest distance, that's this one. The very smallest distance is 25, and the New York Mets. So the 25 is probably the Yankees. So the closest two teams are the New York teams. The second two closest teams are the Chicago White Sox and the Chicago Cubs.
Okay.
The third closest are San Francisco Giants and the Oakland Athletics. Los Angeles and Los Angeles. Then finally Baltimore and Washington.
They all in the same state.
All right, I'm going to run average nearest neighbor again, but now I've selected just these teams in the Northeast. Do you think that they'll be more random or more dispersed than the United States as a whole?
I would think it'd be more random.
I think it'd be more fun.
More clustered.
Yeah.
Okay. Yeah, I forgot to give that as an option. So these numbers actually are further apart. Let's see what it says. So they are actually more dispersed according to the numbers. So that's why you do the numbers, is because you can then, report an actual value. And not only that, they're significantly at the, basically this is the bell-shaped curve, is telling you that this value is significant to the, what is this, 0.10? No, 0.05. So in other words, there's a 95, that a pattern like this will only be created at random, like less than 5% of the time. So this is more likely a dispersed pattern. In other words, the pattern was created by dispersion. The process that's creating this does have a second order property associated with it. In other words, in this area of the United States, there's a significant second order property that's causing these teams to not be all right next to each other. Right? And so in the whole United States, we didn't see that. In other words, they were random. Probably because there's large swaths of land where there's another factor, which is people. So actually the absence of people is making it more random than the presence of people, right? So when there's lots of people, they'll tend to be regularly spaced.
Right, okay, I see what you're saying. I see, because I was looking at that chart,
So
when
that's
you
how
said
you
the
draw that
charts.
conclusion.
And,
Now, we could look at other things, and we might see that they're more clustered. Okay.
Like you probably took
California.
just the state of California.
Yeah.
It might be clustered.
Oh yeah, you're probably right. It's probably all the West Coast, right? Because so if I select just these guys and I run it, well, they're dispersed.
wow.
That's interesting. Now, next week we'll do some other analyses that we'll do this differently. But this is just talking about. It doesn't know. It doesn't see the space at all. It's just doing these distance pairs. And so there happens to be 1 and then 2 and then 2 and 1. And so there is a fair bit of distance between these two. And so there's some large numbers and some small numbers, and it's just getting the average distance between and comparing that to what they would be if they were spread out in regularly spaced intervals. And so it's considering that they're
Right, they are still ours. So that,
yeah. There's probably not enough of them to be. Let's look at people. Let's look at the large cities.
yeah. It's hard to get a pattern
We do
from the
California
guys
and the
like
large
that.
Yeah, it is. It's actually not significant. But if we did the large cities and we generate our report. Oh, also you can actually force it to do a certain area, which actually might help on this one, because by default it's just going to get the extent.
Right.
It's going to take the maximum x, the minimum x, the maximum y, and the maximum x. By default, it's just going to draw a square around that area. Okay. And so the average area does matter, because when it goes to calculate how far they should be if they were random, it uses a box that represents that represents that size. Okay, and so if the box is bigger, they'll be on average they'll be further apart. If the box is smaller, on average they'll be closer together. All right, so I'm going to go ahead and run just the large cities and see what the result is. So those are clustered. The large cities in the United States are clustered together, which is, I think, what you'd expect.
That makes sense.
So I have a question. Can you go back to the
graph?
Yeah, the graph.
I don't know how this got tilted, how this got rotated. Anyway, yeah.
So when we did the baseball teams, we were in the middle of the red section. Like, which one would be more significant, the outskirts? Or
Yeah,
more
the
middle?
further you go this way, the more significant it is.
Okay, so we're very significantly clustered when it comes to our cities then.
Yeah, well, we were right. Oh, yeah, we're very
We're way
significantly
darker.
clustered. Yeah.
Okay.
Now, it would be interesting to see, like, what if we just selected out the middle of the country, which follows central place theory, I think, a lot. I mean, it's used as a model, actually, for central place theory a lot. My guess is that we're going to get at least closer to random, maybe even dispersed for that area. Let's see. Did I actually run it? Large cities. Let me open the table to make sure that it worked. Major League point statistics. No, large cities. No, where's large cities?
I think it's right above baseball.
Open attribute table. Okay, so it did select them. Let's see if the number's less, because it was clustered. It's still pretty significantly clustered.
Yeah.
It's interesting.
Well, you get more of them grouped together in patterns all over.
Yeah, there are some.
Yeah.
Yeah,
Yeah,
Yes. yeah, a lot more groups.
If you took like Arkansas and northern Mississippi, it might be more dispersed.
Like this area right here. Yeah. Of course, we're kind of cherry picking now, right?
Yeah.
But it would be interesting to see it. So now those are more random. Those cities. Maybe even just like right here is pretty random.
I think it's snuck off of the golf cart in that one.
Oh, look, that one's pretty dispersed. That pattern. Yeah, the southeast, which is, I mean, I think that's kind of interesting. Of course, you know, if you go, like I grew up out west, so if I drive from where I live up to where I went to school in Utah, you know, one might see some city, like it was Las Vegas, I see a bunch of cities there, and I go forever without seeing anything.
Right.
And then, you know, there's St. George, and then you go forever, and then, anyway. But you drive here, and there's a little town every once in a while.
Yeah.
You know, so this isn't really looking at little towns, it's looking at big towns, but it was saying that in our area in the southeast, the cities are more dispersed than they are in other areas. You know, we cherry picked one area in the Midwest, and it was random, and we did the whole United States. It was clustered. Okay, so this is the first introduction to that, and there's some other more robust and but also computationally more complicated that we'll talk about the next time we meet for doing this.
But plus in the Midwest or coastal West, it's more like what's that kind of sparsely spread out, random because they don't have that because of the terrain. Keep the city.
Oh yeah, yeah. Like the reason why I didn't select any of this area is because a lot of the pattern here is, well, you've got all the cities that exist on the fall line, you know, right on the edge of the area where there's no more significant waterfalls, and so you could make you could have a little boat that gets up there. And so in the southeast, there's a lot of settlements. You know, Columbia, South Carolina, Atlanta, in central South Carolina, I mean central, Raleigh, Durham, that area. What do they call that? The Research Triangle.
Right.
So you got that cluster, and then you've got the cluster along the coast, and then you do have some more what do you call it? Random or even dispersed settlements in between there. But yeah, this area though is mostly. I mean, some of that was the Appalachians, but a lot of this area is flat, right? So you expect things to be a little bit more. Okay, so I'm gonna take let's take a 15-minute break. I come back 35 minutes after the hour, and then we'll discuss the lab. All right.